Question number 8. A quadrilateral ABCD is drawn to circumscribe a circle. Prove that AB plus CD is equal to AD plus BC. So we want to see first what circumscribing a circle, a quadrilateral circumscribing a circle means. This means that these lines that are touching the circle, they are touching at only one point. And if they are touching at only one point, then we can treat them as a tangent. We will see how we do it. So here I want to take a dotted circle segment and see how I can prove, or how I can say that this line, the line that is used to circumscribe the circle, are considered a tangent. So I draw a line first here like this. So this line is tangent because this line is touching the circle at only one point. And if I draw one more line that is not a tangent, that means this line is intersecting the circle, or it is going through more than one point on the circle, like this here. And if you notice, if the line is not tangent, if it is touching or intersecting the circle or connecting more than one point on a circle, then this line has actually passed or has gone inside the circle like this. And if this line is inside the circle, just think about it, how would this line inscribe a circle? This line cannot, if it is inside the circle, it cannot circumscribe a circle. So that means this line, these lines, that the lines of this quadrilateral that are used to circumscribe a circle have to be tangents. Only then they can circumscribe a circle. So we will say that these lines are tangent to the circle. And if these lines are tangent to the circle, then point P, Q, R and S are points of contact, because that's where this tangent is touching the circle. And if these points are the points of contact, then we can use theorem 10.2. So if we take this segment SAP, then AS is equal to AP. Let's say this is expression 1. Then PP is equal to PQ. Let's say this is expression number 2. CR is CQ. This is expression number 3. And DR is DS. This is expression number 4. Now I want to prove that AB plus CD is equal to AD plus BC. So I take up AB plus CD, and if you look at the line AB, you can break it up into two parts, that is AB plus PB, and CD into two parts, DR plus RC. Now I have to prove that these two sides, the sum of these two sides AB plus CD is equal to the sum of other two sides. So I want to replace these terms, these AP, PB, DR and RC, with the terms of the other side. Then I can prove that these are equal to the other side. So AP, I know from expression 1 is equal to AS, so it becomes AS plus BQ. BQ you can say in expression number 2 is BP is equal to BQ, plus DR, expression number 4, is equal to DS, and RC is equal to QC. And now I rearrange these terms and I bring AS and SD together, because then they will make one side, that is AD, plus BQ and QC together. And AS plus SD, you can see, is AD, plus BQ plus QC is BC, and that's what we had to prove. Question number 9. In the figure, xy and x dash y dash are two parallel tangents to a circle with center O and another tangent AB with point of contact C, intersecting xy at A and x dash y dash at B. I think it should be that when another tangent AB with point of contact C intersects xy at A and x dash y dash at B, prove that angle AOB is 90 degrees. That means I have to prove this angle AOB is equal to 90 degrees. Now I can try using quadrilateral properties here, quadrilateral PQBA, but I don't really see something very special about the quadrilateral. It's just a random quadrilateral. But can I use its interior angle property to prove this angle, to prove that angle AOB is 90 degrees? If I take the sum of its interior angle, then they don't really feature, or I can't really put it in terms of angle AOB. So there is really no use of using the quadrilateral property. Rather, a line that touches O, that connects the point O, that is the center of the circle, to the point C, that's the point of contact that the tangent AB makes, this line, drawing this line, can do the magic for me. I can apply theorem 10.2 very easily if I draw this line. And if I draw this line, then you can see that angle AO is going to bisect angle POC. And how? Okay, let's revisit theorem 10.2. If we draw a circle, and if we draw two tangents from a common point outside the circle, like this here, and if the point of contacts that these tangents make are going to be connected by the radii, like this here, then the angles that these radii make and the angle between these tangents is going to be bisected by this line that is connecting the center and the common point outside the circle. So this line, this angle, and this angle both are going to be bisected. So I can use this theorem to say that AO bisects angle POC. That means angle POA is going to be angle AOC. Similarly, and let's say this is expression 1, and similarly I can say that BO bisects angle QOC. This angle QOC is bisected by BO. That means angle QOB is equal to angle BOC. And this is, let's say, expression 2. And here PQ is diameter. That means the angle, that means a straight line. An angle on the both sides of a straight line is going to be 180 degrees. So angle POQ is going to be 180 degrees. And if you can see here or notice here, then POQ, I can break this angle up into 4 angles, that is POA, AOC, COB, and BOQ. So angle POQ is going to be angle POA plus angle AOC plus angle COB plus angle BOQ, which is going to be equal to 180 degrees. And now I can say that angle POA is angle, I can replace angle POA with angle AOC. That's what I know from expression 1. And why do I want to replace POA with AOC, not AOC with POA? Because I want to prove that angle AOB is equal to 90 degrees. And if I have AOC, and if I have these terms, this expression in terms of AOC and COB, then I can easily prove that AOB is equal to 90. And then I put BOQ, I replace BOQ with angle COB, which is going to be 180 degrees. Then it's twice the angle of AOC plus twice the angle of COB is equal to 180 degrees, and I take the 2 out. It's angle AOC plus angle COB is 180 degrees. Then I divide both sides with 2, and it becomes 90 degrees. So angle AOC plus COB is 90 degrees, and if you Look at the figure and see AOC and COB is angle AOB, this here. So this is angle AOB. That means angle AOB is 90 degrees, and that's what we had to prove. Problem 10. Prove that the angle between the two tangents drawn from an external point to a circle is supplementary to the angle subtended by the line segment joining the points of contact at the center. That means if you draw a circle like this here and its center is O, and if you locate a common point P outside the circle, and let's go back to the question, that prove that angle between the two tangents drawn from an external point. So let's first draw two tangents from an external point P, and let's say these tangents touch the circle at point Q and are from an external point to a circle is supplementary. So this angle QPR, is supplementary to the angle subtended by the line segment. Well, it says line segment, so is it going to be a single line? Actually, it should be line segments. Only then I can say that I can locate a point outside P, outside the circle P. I'll show you in a moment how, why and how. So line segment joining the points of contact at the center. In these lines are joining the point of contact at the center. So angle QOR, the angle subtended by these lines is angle QOR. The question says sum of angle QPR, that is this angle, and the angle QOR, that is this angle, should be 180 degrees. Why? Because the question says these angles are supplementary, and supplementary angles add up to 180 degrees. That means their sum is 180 degrees. Now let's say this line segment problem here. If it's a line segment, that means it's a single line joining the points of contact at the center. If it is joining the point of contacts at the center, that means the tangents are always going to be at the boundary of the circle. So if it is joining the points of contact, that means this is going to be a diameter from one end of the circle to the another end, passing through the center. And if you draw these tangents here, we have already proved that these tangents at the endpoints of a diameter are always going to be parallel, and if these tangents are parallel, then they are never going to meet outside the circle. So point P is not possible, so we cannot draw two tangents from that point. That means this term line segment has to be line segments. Then I can draw two line segments QO and OR. Now we know that the QPRO is a quadrilateral, and first let's say the interior angles of this quadrilateral are angle 1, 2, 3 and 4, and the sum of these interior angle is going to be 360. Let's say this is expression 1, and if you remember theorem 10.1, then the radii on the points of contact are always going to be perpendicular. So angle OQP is going to be 90 degrees and angle ORP is going to be 90 degrees, and we can plug in these values in expression 1. So angle 1 is 90 degrees, angle 2 we do not know, angle 3 is 90 degrees, angle 4 we do not know, and their sum is going to be 360. And when we calculate this, it is going to be angle 2 plus angle 4, and angle 2 is angle QOR and angle 4 is angle QPR, and they add up to 180 degrees, and that's what we have to prove. Question number 11. Prove that the parallelogram circumscribing a circle is rhombus. So a rhombus is a quadrilateral that has all its sides equal, and a parallelogram is a quadrilateral that has its opposite sides equal and parallel. Now let's try circumscribing a circle within a parallelogram. So this is a parallelogram, and if this quadrilateral or parallelogram needs to circumscribe the circle, that means the line of this parallelogram needs to be tangent to this circle. So let's say this circle has center O and the points of contact that these lines make at the circle are point P, Q, R and S, and let's say this parallelogram is ABCD. Now we are given that ABCD is a parallelogram. That means this opposite side DC and AB are going to be equal and parallel, and then the other set of parallel sides CB and AD are going to be parallel and equal. Now you know that points A, B and CD are the external points from where we have drawn tangents that are meeting at touching the circle at point P, Q, R and S. So we can apply theorem 10.2. That means AS is going to be equal to AP, BP is going to be equal to BQ, CR is going to be equal to CQ, and DR is going to be equal to DS. Now I want to take one side of this parallelogram and also the opposite side of the parallelogram and break it up, and then put this line in terms of the line adjacent to it, so that I can prove that two adjacent lines of this parallelogram are equal, and when two adjacent sides are equal, then I can easily prove that all its sides are equal. Let's see how. So I take up side AB and I can say that this line is AP plus PB, and I know that AP is also equal to AP and PB is also equal to PB is equal to QB. Let's say this expression 5, and DC is DR plus RC, and DR is equal to DS, and RC is equal to QC. And let's say this is expression 6. Now I add expression 5 and 6, so it becomes AB plus DC. That means AS plus QB plus DS plus QC. Now I rearrange these terms to put them together to make up a side. Say I put together AS plus DS and QB plus QC, because then I can treat them. Then I can say that these terms make up a side. So AS and DS is going to be AD, and QB plus QC is going to be BC. And now you know that AB is equal to DC because they are opposite sides of a parallelogram, so they are going to be equal. So I can say that it is, I can also write it as AB plus AB because this is equal to AB, and AD and CB are equal. Why? Because they are parallel side, because they are the opposite sides of the parallelogram, so they are also going to be equal. So I can say this is BC plus BC. That means 2 times AB is going to be equal to 2 times BC. That means AB is going to be equal to BC. Now you know AB is equal to DC. That means BC is also going to be equal to DC, and BC is equal to AD. That means AD is also going to be equal to AB. That means all its sides are equal, and if all the sides of this parallelogram are equal, then this parallelogram or this quadrilateral is a rhombus.